Hello ladies and gentlemen, I am Dr. Claudia Albers, Planet X researcher and professional physicist. And today I'd like to talk to you about another one of my articles. This one is entitled Complex Plasmas and the Liquid Sun. And complex plasmas can occur in the solid and liquid phases. And this is actually very important in understanding some details regarding the stellar remnants that have been observed in the inner solar system and close to the Sun. Now, these complex plasmas, and another name for them is dusty plasma, are formed when microparticles, sometimes called dust particles, so these are very small particles about the size of 1 micrometer, are added to normal plasmas. And what results is a plasma that develops a crystal structure, and so can occur in the liquid and solid phases. Now, some of the stellar remnants observed in the solar system are quite large, and one of the largest one was the blue stellar remnant, which was first photographed by Scott in May of this year. And this object clearly had a solid surface, and we could see that it was solid because it had grooves in that surface. And only a solid surface can possibly have these grooves, because if it was liquid, the liquid will fill in the grooves, and if it was a gas, of course the gas would occupy any space. So it is solid, and it looks dense. However, it did have some material attached to that surface which did not seem to be as dense, but yet seemed to be solid, or at least semi-solid. And this stellar remnant was shedding that material. As you can see, there was a large hole here, and it was obviously ionizing it, or turning it into a gaseous plasma, and you see it here. It's present between the object and the Sun, so it looked like it was exchanging its own plasma, which it was changing into a gaseous plasma from this material that was attached on its surface. And I believe that material was its part of its envelope. However, this object did not seem to have much of an envelope left, and it seemed to be shedding the last bit of it. Then we can see that these objects have a particle flux transfer with the Sun. We can see in this image, this is the blue stellar remnant. You can see the grooves in the surface. You can see the material attached to it. You can see plasma in the gaseous phase attached to its surface. There's this magenta one, and there's this yellowish one, and it's exchanging material with the Sun. This is the Sun's corona, and you can see this plasma connection between the two objects. So it was obviously exchanging. Now, these stellar remnants are, of course, stars. Only stars would be at home in such an extreme environment as the Sun's corona, which is at a temperature of between 1 and 3 million degrees Kelvin. A normal planet would not survive being in that environment. So these are objects that were once main sequence stars, and then went through an aging process where they turned into red giants, and then they became white dwarfs. After that, they cooled down even more. They lost more energy, and eventually they were only able to emit infrared light. At least most of them seem to be in that state when they enter the solar system. However, after drawing plasma from the Sun and energy, possibly through their magnetic connection with the Sun, they are rejuvenated, and they appear to be able to emit light once again. Now, the fact that we see this object hovering almost stationary with respect to the Sun is very surprising, because if there was a gravitational interaction between the two objects, what we would expect is for this large object to collide with the sun. Either that or whichever one is the lesser mass would go into a very fast orbit around the other one, but this does not happen. So this means that the gravitational interaction does not seem to act at all between these two bodies. And if that's the case, we have to question whether the gravitational interaction is actually a force that acts at any time in the universe. These objects obviously connect magnetically, and perhaps the magnetic force is the force that is causing these objects to be attracted to each other and to interact with each other, and maybe actually the force acting on the inside of stars, holding them together as such. We do know that the magnetic force is what is responsible for the Z-pinch effect, which gives birth to stars. It contracts them into and attracts plasma to one single point. So the gravitational model is still useful for calculating orbits and periods within the solar system, but it does not seem to actually be the force that is acting between models. Of course, both forces, the gravitational and the magnetic, are inverse square laws, which means that they drop off as the distance squared between objects, and that's possibly why the gravitational model may, in certain cases, approximate the actual force acting, which may, in fact, be the magnetic force. Now, we do know that these objects absorb energy from the sun, and the way this has been observed was with the first stellar core observed that I have observed in the solar system, and that was the 2007 stellar core. And this object emitted light from its ionization envelope. And you can see the object here. This is from stereo B, and this is core 2, and from February 20th, 2007. This is at 8:03, this is at 9:03. So as we move along from image to image, the object is getting closer to the sun. It was approaching the sun at that time. And also what we observe is that it gets darker and darker. Notice here that it is emitting light from its envelope on the side opposite to where the sun is, so this cannot be a reflection of light. This is actually the object emitting light. And if we were to look closely, it has a dark core, and this is the envelope around it. And the envelope was ring-shaped. That's why we could see the core through this top portion. And the object becomes darker and darker as it approaches the sun, and this suggests that it goes from energy emission to energy absorption as it approaches the sun. So this is what happens when an object goes from emission to absorption, and we can see that on Earth. We can, for example, if we have a wall that is being sunlit during the day, and if we touch that wall, it will not, or if we stand next to the wall, we will not feel heat coming off it, even if the surface seems hot to the touch. But as soon as the sun goes down, if we stand next to the wall, we can actually feel heat coming off the wall. This is the radiation that's coming off the wall, because the wall has turned from absorbing sunlight to emitting radiation, in this case thermal radiation. So this is what happens with energy emission and energy absorption. So this is quite clear that these objects are able to absorb radiation from the sun. It could still be through a magnetic connection. Even from this distance, it could be that there was a particle flux transfer between the sun and this object. Now this particle flux transfer is illustrated with this image, and these objects have very strong magnetic fields, and the reason for that is because they were once white dwarf stars, and white dwarf stars have very strong magnetic fields. This is quite well known. This is probably due to the fact that they lose most of their outer layers of material, and then the ionization layer moves way down towards the core, and it's right around the core, and this has the effect of possibly due to conservation laws such as conservation of angular momentum, or it could just be that the surface area of the object has decreased to such an amount that it greatly increases the potential energy on the ionization layer. Either way, these objects are known to rotate very fast, and they are known to have very strong magnetic fields. So when of these objects comes close to the sun, they pull on the sun's magnetic field, and the sun's magnetic field lines are then perpendicular to the surface of the sun, and if we were to look at them close to the sun, they look like open field lines. But magnetic field lines have to form closed loops, so they have to close somewhere. So this means that solar ionized particles spiral along these outgoing field lines towards the stellar core, and ionized particles from the stellar core move along the returning field lines towards the sun, and this creates a particle flux transfer between the two objects. This is also what leads to coronal holes. Now, the fact that these stars have ionization envelopes puts into question where the sun is made out of gas. Now the sun, these are stars, the sun is a star, and we do know that the sun has a corona, and the corona is a plasma in the gaseous phase. We know that it parts as objects move through it. However, the sun has what's called a photosphere, and this surface seems to be boiling and flowing, so it may actually be in the liquid phase. And now that we know that we can have plasmas in the liquid phase, it's very likely that the photosphere is a liquid or a semi-liquid. It may, or some parts of it may be solid, because we have what are called sunspots, and the only way we can have holes in the surface of the sun is for at least part of it to be solid, because if it was, the whole thing was liquid, any holes would just fill in. So how is it possible to for the sun to have a liquid surface? Well, so far the theories about the sun have said that the whole sun, right down to the core, is a gas, and that would mean that it has a very dense core, and the other thing is the whole matter of the sun would be in the gaseous phase. But how do we then describe the sun as boiling and erupting? Because boiling and erupting seems to require a liquid layer. Now, the other reason why the sun may have may be described as liquid, and why it may seem to be liquid, is the fact that there are seismic waves that travel along its surface, and seismic waves are not supported by a gaseous phase material, only by liquids and solids. So it's possible, therefore, that the sun is in fact a liquid sun, or at least its surface is liquid. Some of its layers below that may be more solid. But we do require at least part of it to be in the solid phase in order to have sunspots that are holes right through the photosphere. The photosphere is 500 kilometers deep, and to have holes right through it that are not filled in would require at least that area to be somewhat solid. So the accepted value for the sun's core is 150 grams per centimeter cubed, and this is therefore extremely high and possibly not what the actual value is. This is what it is required if the sun is made up of a diffuse gas. But the sun's average density is 1.4 grams per centimeter cube, which is just a little higher than the density of water at 1 gram per centimeter cube. And this suggests that the sun is therefore mostly liquid because of this close match between the density of liquid water and the average density of the sun. Now, this would also explain why any force that would try to compress the sun, and we usually, at least most of the theories suggest that the gravitational attraction would lead to the sun collapsing because it's made out of gas. But now that we know that it's not made out of gas, or probably not, so it's made out of solid and liquid. And since solid and liquids are incompressible, it becomes clear why the sun does not contract any further when it is under pressure from a compressing force, be it the gravitational attraction or the more likely case of the magnetic force, which would compress it into a solid sphere or a spherical object. Now, gas giant planets like Jupiter actually have densities close to the density the sun has. For example, Jupiter has a density of 1.33 grams per centimeter cube, just a little lower than the sun's average density. So if the sun has a core that is possibly not that dense, and it is in fact made out of liquid and solid plasma, it is likely that Jupiter as well is made out of liquid and solid layers, or possibly a thin outer layer that is gaseous. And the same thing would probably apply with brown dwarfs. However, I would rather go in the direction of saying that most brown dwarfs being studied are not actually brown dwarfs, such as, in other words, substellar objects. They seem to actually be stellar remnants. At least quite a few of them seem to be, because they have characteristics of stellar remnants. For example, they have clouds of ionized gas in the vicinity surrounding them. And it takes an object going through the red giant and the white dwarf phase to have these kinds of clouds of ionized gas, which come from the outer layers of the star in the main sequence phase. And these layers move away from the star or accelerated away from the star, and possibly through the the electric field the object produces. And therefore these objects become white dwarfs with a cloud of ionized gas around them, and these clouds are often irregularly shaped and diffuse. So the presence of these ionized clouds always makes me think that these objects are in fact stellar remnants that have gone through the white dwarf phase. But they have other characteristics, such as fast rotation, which we associate with the white dwarf phase as well. And some of them have jet ejections. We see here this is a brown dwarf HH1165, and it has a huge jet plasma ejection. And the stellar remnants in the solar system also have these types of ejections, As you can see, this object has a plasma loop ejection and a jet ejection, and there's another one there with a jet ejection, and we see the same in this image over here. So these are not planets. Planets cannot have plasma ejections because they do not have hot plasma. So it takes a star to be able to have the hot plasma necessary to have these types of ejections. And these are therefore the stellar remnants in the inner solar system. And because we can see they have this kind of ejections, it suggests that objects like these, which are called brown dwarfs, may in fact not be brown dwarfs but stellar remnants, or as I used to call them, brown dwarf stars, objects that were once main sequence stars and have aged. So, in conclusion, stellar remnants in close proximity to the Sun have solid cores, and the material in their ionizing envelope seems to be less dense but at least semi-solid. The Sun's photosphere also seems to be an ionizing envelope, and it seems to be in a liquid phase with perhaps some parts in it in the solid phase, such as areas where sunspots occur. This can be understood in terms of complex plasmas, which can exist in the liquid and gaseous phases. I am Dr. Claudia Albers, Planet X physicist. Thank you for watching.